Now, students, you see that is weight of the reactant is 500, weight of the product is 499.99, which I took it as approximately 500. Now, definitely a question is coming into your mind. That sir, it is 499.99, it is approximately 500, but it's not 500. So, where that 0.01 gram mass has gone, where it has gone? Now, this answer was not provided by Landolt or by what you can say Anthony Lavoisier. So, this is the, I should say, this is the drawback or the limitations of this particular experiment. Okay. So, what you find is that is Einstein explained this particular thing. Einstein said that here what is happening in ordinary chemical reaction, this particular thing is not going to take place in ordinary chemical reaction. Ordinary. This is an ordinary chemical reaction. Alright, this is an ordinary chemical reaction. What you find is that here, this particular ordinary chemical reaction, that is almost it will be 500 gram, almost it will be 499.99999, almost we will take it as 500 gram. In ordinary chemical reaction, it is the mass, the loss in mass is very negligible, very negligible, it is very negligible. But listen carefully, in some other reactions, like some nuclear reactions, the mass is being converted into energy. Alright, now listen carefully what I said. In other reactions, that is in other chemical reactions, like in nuclear reactions, the mass is being converted, the loss in mass is being converted into energy. According to Einstein's mass energy relationship, that is E is equal to delta mc square, but delta m is the loss in mass. Loss in mass means 500 minus 499.99 into, that is c is the velocity of light, 3 into 10 to the power 8 meter per second square. What Einstein said? Einstein said that you have stopped convection because by closing the air hole, by making it airtight, but we did not stop the radiation. When the light is falling, because you are doing this experiment in what you can say in sunlight or in ordinary light, you will be doing this experiment in the lab. So when the light is falling upon it, some amount of energy is being radiated from the walls of the, what you can say, that particular Landauer's tube. Some amount of energy is being radiated out from the walls of the Landauer's tube, from the walls of the H tube, that's a glass tube, we can say that. Got it? In the form of, what you can say, radiation. So when some amount of energy is being radiated out, so what is that? The loss in mass is being converted into energy. What I said, I think it's clear to you that where that loss in mass has gone to, that is 0.01, where it has gone, that has been converted into energy according to Einstein's mass energy relationship. Because when the light is falling upon that particular glass tube, then the energy is being radiated out from the walls of the glass tube. Energy is being given out from the walls of the glass tube. In the form of energy, it is being given out. So hence there is a loss in mass. But again I repeat, this reaction is only possible in a nuclear reactions or some other reactions, but it is not possible in ordinary chemical reactions. So Einstein also added it that whatever the Landols and what you can say this Anthony Lavoisier said, it's absolutely correct, because they said on the light of ordinary chemical reaction. Ordinary chemical reaction, the reaction which is occurring in our day-to-day life, or the one which you are doing it in the lab, that is your displacement reaction, double decomposition reaction, decomposition reactions, addition reactions. Got it? For ordinary chemical reaction, this is not being possible. So this was the drawback of this particular experiment, that is a law of conservation of mass. So based upon that, now the law has been slightly, what you can say, modified. So what is being said that the law is said that the mass and the energy are interconvertible. You know that mass and energy both are interconvertible, as you can see there, that mass is being converted into energy. As mass and energy both are interconvertible, but the total sum of the mass and energy during any physical or chemical change remains constant. What I said, the mass and energy are interconvertible, but the total sum of the mass and energy during any physical or chemical reactions remains constant. Alright, this is the alternate definition now it is being given, that is on the light of Einstein's mass energy relationship. Otherwise, when the definition will be asked to you for the law of conservation of mass, the initial one which I have told you, that you will be writing it out. I think it's clear to you, the first law, the law of conservation of mass. Fine. Now, next is, after that we'll come to the next law, the law of definite proportion or the law of constant composition. Now, what is that? Law of definite proportion or law of constant composition. Now, this law, I told you already, it was given by Joseph Louis Proust, J.L. Proust. So, what is the definition of this law? So, the law states that in this way, that when a reaction is taking place, when a chemical reaction is taking place, alright, then what we find is that the product which is being formed, in any particular chemical reaction, the ratio of the weight of the reactant is always constant. The ratio of the weight of the reactant remains always constant. Alright. So, in this way you can say that in any particular reaction, that is the mass of the product which is being formed. Alright, the mass of the product which is being formed, in the mass of the product, the reactants which are combining to form the product, that is a compound. So, the reactant always combines in a simple whole number ratio by mass, and that particular ratio remains always constant. Alright, that remains always constant, we can say that. Okay, fine. Now we will explain this particular one further by taking an example. We can say that. That is law of definite proportion. We will explain it. See now. So we are taking here, that is calcium carbonate, let us say. On heating it gives calcium oxide plus carbon dioxide. Now we are taking calcium nitrate, let us say. On heating it will give you calcium oxide plus nitrogen dioxide plus oxygen. Alright, 2CaO plus 4NO2 plus O2. So in both the case you are getting calcium oxide, let us say. Alright. So now what you find is that calcium is to oxygen. What I said in the law? That when a compound is being formed, when the product is being formed, the weight of the element which is being present here, their ratio is always simple whole number ratio. Now calcium oxide, what is the weight of calcium? That is atomic weight is 40, and oxygen is how much it is? Nothing but 16. The 40 is to 16, so 2 into 8 is 2 into 20, 2 into 4, 2 into 10, then 2, 5. So ultimately what is the ratio you got it? 5 is to 2. So now here what I can say is that, listen carefully, in whichever source you collect calcium oxide, from whichever source you collect calcium oxide, the ratio of calcium is to oxygen. Alright, this is the ratio you got it for calcium is to oxygen. The ratio of the calcium is to oxygen is always fixed in calcium oxide. The ratio of calcium is to oxygen is always fixed, that is 5 is to 2 by weight. For example, you are preparing carbon dioxide. Carbon plus oxygen gives CO2. Carbon monoxide plus oxygen will also give you CO2. Alright, like calcium carbonate on heating also will give you CO2. So the ratio of carbon is to oxygen in CO2 from whichever source you collect, that is the ratio will always be constant. Let us see this also, carbon dioxide. So carbon is to oxygen, is how much? Now here carbon is 12, oxygen is 32. So 4 into 3, 4 into 8. So what we got the ratio? 3 is to 8. So from whichever source you collect carbon dioxide, whether by heating calcium carbonate, whether by heating carbon and oxygen, whether by heating carbon monoxide and oxygen, from whichever source you collect, the ratio of the element is always fixed, it is constant. Here also it is being fixed, it is constant. So we can say this in this particular way. The definition we can say in this way also, that any pure chemical compound, listen carefully, you may write this definition also. Any pure chemical compound, regardless of its source, always contains the elements in a fixed proportion by mass. Again I repeat, any pure chemical compound, regardless of its source, contains the elements or combines the elements in a fixed proportion by mass. We can say that, or by weight, we can say. Clear? So in this way, I think it is clear to you that from whichever source you collect, the source is not important. Alright, it should be a pure chemical compound. the ratio of the element in which the compound is being present, the compound is being formed, is always fixed, it's always constant. We can say that. Now, to what you can say experimentally verify this law, we will do an experiment. We will see an experiment. Okay? Children, are you following what I am saying? I think you are getting me. Alright? So, now see here. What we will do is here, we will take here copper carbonate and we will take here, that is copper nitrate. On heating, now copper carbonate, remember that it is green in color and copper nitrate, it is blue in color. Correct. So, you will be heating copper carbonate, you will get copper oxide and carbon dioxide. Okay. And copper nitrate on heating will give you copper oxide plus nitrogen dioxide plus oxygen. So we'll balance it, this one, you got it this. Now you got a black residue on heating, both. This green color substance, you got a black residue, this blue color substance, you got a black residue. Now you take equal weight of copper oxide from copper carbonate and copper nitrate. Let us say I have taken 20 gram of copper oxide. Whatever the weight you will be getting it here, the residue, from there you take 20 gram of copper oxide. Okay, you take 20 gram of copper oxide and through this copper oxide you pass a dry hydrogen gas or a current of hydrogen gas, you pass it, you heat it. Okay, now what will happen? Hydrogen is a reducing agent, it will reduce copper oxide to copper and water. How will you know that the reaction has taken place? Like here you got a black residue, so you came to know the reaction has taken place. Here you will be getting a reddish brown colored residue, or brown also you can say that, because copper is reddish brown or brown in color, we can say. So once you get this residue, you come to know the reaction is completed. Fine. Now what I said, from both the source you take 20 gram and you heat it and you pass it through hydrogen gas. You will get copper. Now you weigh the copper from 20 gram, how much copper, 20 gram of copper oxide, how much copper you got it, to weigh it. Got it, to weigh the copper from both the source. Are you following what I am saying? 20 gram, each you have taken, you have heated through hydrogen, you got some copper. You will get some weight of copper. Now from copper oxide you subtract the weight of copper. Alright, from 20 gram you subtract the weight of copper. What you will get? The weight of oxygen. First only you got the weight of, what you can say, copper. Now you got the weight of oxygen. Now you got, what you can say, 2, that is ratio you got it. Copper is to oxygen from copper carbonate, the copper oxide which you got it, and from copper nitrate, the copper oxide you got it. The 2 ratios you will be getting it. The 2 ratios will be equal. It will be same. Alright, once more I am saying you. From here the residue which you got it, you take 20 gram of copper oxide from it. Got it? 20 gram, and you heat it, this one. Each separately you heat it. You will get copper. You take the weight of copper. Got it? From both the source which you got it. And you subtract from 20. You will get what? Weight of oxygen. From copper oxide, if you subtract copper, what you will get? The weight of oxygen. Now you find the ratio between copper and oxygen. What is the ratio? From both the source which you will be getting it, the ratio will be the same. Alright, it will be same. So from this experiment, it is being verified that the ratio of copper is to oxygen, got it, from the different source which you are getting it, is always remaining the same. We can say that. Clear? In this way. Now, but this experiment has also got limitations. Now, the limitation of this particular experiment is that, now this particular, what you can say, experiment is true, or as I took carbon dioxide, the experiment, you can see that in case of carbon dioxide, I got the ratio carbon is to oxygen, how much it is? 3:8. If you remember it, I have taken the atomic weight of carbon as 12, if you remember it. Clear? But now this law, as I was saying you, the limitations of this law is that this law was true up to 19th century. Now after 19th century, around 1913, we can say that Soddy, who was an English chemist, who discovered isotopes. After the discovery of isotopes, what he finds is that, now here I have taken, which isotope of carbon I have taken, it is that carbon 12. But you know that carbon exists as C13 also and C14. Of course, they are not stable. C14 is the radioactive isotopes, you must be knowing it. Of course, they are not stable. The stable isotope is C12. Alright. So, if you take C13 or C14 here, the ratio will be different. The ratio will be different. For example, what I am doing is that I am rubbing it first, this one. I am rubbing it first. So, for example, what I am doing, carbon dioxide, I am taking carbon is to oxygen. Let us say carbon is 14 and oxygen is 32. Alright, here I have taken carbon is oxygen, carbon atomic weight as 12. Here I am taking it as 14. Now see, will it be same? It will be different. So here it will be 2 7s, here it is 2 16s. So what you got the ratio? 7 is to 16. Now if you take carbon is to oxygen as C13, what you will get it? 13 is to 32. Alright, 13 is to 32. Is the ratio same? Here you got it 3 is to 8. Here you got 7 is to 16. Here you got 13 is to 32. The ratio is not the same. So this law is valid for those elements which does not show isotopes. But again I repeat, here we will be taking that particular isotope only which is being stable. So remember that C6C12 is a stable isotope. 6C13 and 6C14 we are not taking it because they are not the stable isotope, they do not form carbon dioxide. Alright? But that is one of the limitations I said you. Now this law is also not true when the compound shows what you can say isomers. Alright, when it's so isomers. Isomers means, now let us say you are taking the molecular formula of the compound as, let us say C2H6O. Now C2H6O can exist as C2H5OH and it can exist as CH3O CH3. This is your ethyl alcohol and this is dimethyl ether. You might have studied in class 10. Isomers. Alright, isomers are the compound having the same molecular formula but different structural formula. We can say that. Alright, so here it is ethyl alcohol and here it is dimethyl ether. It's an ether and it's an ethyl alcohol. So what I said you, that is here, if I take ethyl alcohol and do the experiment, it will be different. If I take dimethyl ether and do the experiment, it will be different. Alright, because they are two different compounds here, it is two different compounds, but the molecular formula is the same. Alright, if you take the molecular formula, okay, the ratio which you are going to get it's correct. But if you take two different compounds, if you take the structural formula, then it will be different. So again the limitation of this law is that this law is not valid for those compounds which shows isomers. That means it is not valid for organic compounds because organic compounds shows isomerism. We can say that. Alright, so these are the limitations of this particular law. That is a law of definite proportion or constant composition. So again I repeat the law, the definition, that any pure chemical compound regardless of its source is always made up of the same elements combined together in a fixed proportion by mass. The ratio remains always constant. Got it? But again I repeat, in carbon dioxide which I gave you the experiment, that is there you must take the stable isotope. Alright, you must take the stable isotope and do it. Then you will get the answer to be as correct. Thank you.